So here we are. We want to program Hero Jr. We want to write code for a consumer robot from the 1980s in its native machine language. And this book does not hold the answers. It does have a few useful routines from the robot's ROM that we can use to do things beyond just playing with the robot. We saw the one to measure distances with the sonar sensor in a previous video.
5.9.
There are a couple of other useful ones, like the routine at CFB3, which allows us to change the date and time of the real-time clock, or its companion at 84C4, that lets us change the special day. Let's try that one now so we can recall how to use the robot wizard.
Ready. Robot wizard. A4C4. Press enter to confirm, or C to change. Enter. Set special date. Enter date. Month. 0, 7, 8. 09 year. Don't care. July 9. Press enter to confirm, or C to change. Enter. Ready.
There's a more complicated procedure to change the robot's or user's name that contains multiple steps. Let's try one of those. To begin, we'll check the robot's current name using Speak and selection 04.
I am Hero Jr., your personal robot.
If Hero Jr. speaks that phrase from its read-only memory, how is it that we can change its name to something new? Here's how it works. Speak 04 is accessing the sentence in three parts. The first and last parts are directly referenced in the ROM memory, but the middle part, the robot's name, is not directly accessed. Instead, the speak routine looks at a RAM memory location for a pointer to the name. During the setup routine, that pointer is set to the Hero Jr. phrase in ROM memory, but the pointer itself is in RAM, so it can be changed. The pointer is at location 03BE in RAM, so we can use the robot wizard command at F5C4 to change it to point somewhere else.
F5C4. Press enter to confirm, or C to change. Enter. Enter address. 03BE. Press enter to confirm, or C to change. Enter. Enter bytes next. 05 next. B6 next. Ready.
With that done, the situation now looks like this. The pointer at 03BE now contains the address 05D6, which is a location in RAM that can safely store our new robot name without being overwritten by the rest of the robot's operating system. It's a safe place in memory. The only problem is, it does not yet contain any phrase information. We'll look at this in more detail later in the video, but the voice synthesis chip in the Hero Jr. uses a stream of phonemes to generate sounds. We can represent them as either phonetic symbols or their matching hexadecimal numbers. Let's change the robot's name to RT1. Phonetically, RT1 looks like this. And these are the matching hex values for each phoneme. The PA zeros at the end of each line add a short pause between each word, and the final FF marks the end of the sequence. Now we just need to enter those numbers in RAM, starting at 05D6. Back to the F5C4 robot wizard routine one last time.
Enter address. 05D6. Press enter to confirm, or C to change. Enter. Enter bytes next. 1, 5 next. 3, 1 next. 3, 8 next. 0, 3 next. 2, 8 next. 3, C next. 2, 1 next. 2, 9 next. 0, 3 next. 2, B, next, 3, 2, next, 3, 1, next, 0, B, next, 3, F, next, F, next. Ready.
And finally, we can hear the results of our labor by running Speak 04 again.
0, 4, INRT1, your personal robot.
Changing the user's name is done the same way, but its pointer is located at 03C0, and we store its phoneme pattern at 05F7. The programmer's guide has a list of male and female names with their matching hex numbers, but later in this video we'll learn how to encode any word we want from scratch. There are some other routines in here as well that we'll use in future videos to adjust some sensors and check the RS-232 port on the back of the robot, but that's about it. As I said, this book has no actual programming. So where does that leave us? How do we code for a 1980s consumer robot that was never really intended to be programmed? With a little research, a little luck, and a lot of reading between the lines, we'll be writing machine language for the Hero Jr. in no time. Besides, ML is practically my middle name. So here is the challenge. We'll learn to program the Hero Jr. by creating a version of the Hello World program of computer science fame. But I want it to work on an unexpanded Hero Jr. with only 2K of memory. I don't want to use an external cartridge to run a high-level language like BASIC or HPL. I want to do this with just the Hero, some data sheets, some graph paper, and of course a Papermate Sharpwriter No. 2 pencil with the lead not retracted. To pull this off with an unexpanded Hero Jr., we need three things: a safe space in that precious 2K of memory that isn't used by the operating system, a method of getting instructions and data into that safe space, and a way to run the program when we're done. Believe it or not, we've already seen all three when we changed the robot's name. The same location where we stored the RT1 phrase data can hold our program instead. In fact, if we run over into the area set aside for changing the user's name, we can get around 60 bytes of safe space, which should be more than enough for our code and data. So we'll start our Hello World program at 05D6. We've been using the built-in bootloader program from the ROM all along. It's the routine at F5C4 that lets us enter bytes into memory. We'll use it to enter both our program and the Hello World phrase. And finally, the run command should be familiar to you by now.
Robot wizard.
It's literally the ROM routine that asks for an address in memory and runs the routine that resides there. And now, with our three things taken care of, we can start to write our first machine language program for the Hero Jr. Before we get to the actual code, let's take a high-level look at the Hero Jr.'s computer. It essentially has two components, a microprocessor and memory. Let's start with the latter. Think of the memory as a large set of boxes numbered from 0 to 65,535. But it's easier to use hexadecimal numbers, so memory goes from 0000 to FFFF. Each box can contain a single byte, a number between 0 and 255, or in hex 00 to FF. If we need to store larger numbers, we use two consecutive boxes and call that unit of storage a word. Words are useful for storing the addresses of other things in memory. A word can hold values between 0000 and FFFF. The memory contains RAM, ROM, and input-output devices. To the microprocessor, they all look the same, just addresses in memory with values in them. Conceptually, the memory has a mixture of instructions to the microprocessor and data for it to manipulate. The microprocessor, or CPU, in the Hero Jr. is the Motorola 6808. It has an instruction set similar to the 6502 CPU found in a plethora of 1980s home computers, but there are some differences. You can think of the CPU as a set of specialized registers that can talk to each other and to memory. There are two accumulators, called A and B. These registers work with circuitry inside the CPU to do computations on their contents. They each store 1 byte. There's a 2-byte register called X, which is useful for pointing to locations in memory and moving address values from one place to another. And lastly, there are 3 specialized registers we'll learn more about in a future video: the program counter, the stack pointer, and the condition codes register. Now let's see how we'll have memory and the microprocessor work together to have the computer speak the words, "Hello World." We'll be relying on a much-used ROM routine named say phrase. It's such an important routine that it's literally the first program in ROM at location 8000. To use it, we just need to place the address of our phrase data into a variable called phrase_address1, which is in RAM at location 0303. Then we jump to the say phrase routine, and it will do the rest. Once it's done, we return from our program back to the main menu. In plain language, it looks something like this. Put the address of our phrase into phrase_address1, jump to the subroutine say phrase, return to the main menu. And in actual assembly mnemonics, it's not much more complicated. Mnemonics are those 3 or 4-letter abbreviations that stand for the full instruction names. They are useful to the humans writing the program, but they are meaningless to the CPU. A program written in mnemonics is called an assembly language program because it has to be assembled or translated from mnemonic form into a set of numbers. The CPU executes these numbers directly, and they are its true machine language. To start hand assembly of our mnemonic program, we begin with a sheet of graph paper laid out in columns. The address column shows where particular lines of code will be entered in memory. We don't need to enter the address of every line, just the ones we need to reference later. Since we're putting the program into the safe space we identified earlier, I've written its starting address, 05D6, at the top of the address column. Next is the hex column, which will contain the hexadecimal numbers of the assembled machine language program. These numbers are what we'll enter into the robot at the end of the process. The mnemonics column has the human-readable version of our program, which needs to be assembled or translated into hex values. And lastly, the comments column has notes to help us keep track of things. If we were using a computerized assembler program, it would have all these same columns, and it would completely ignore the comments. They are there for us humans, just to make the process easier. Let's start with the first instruction, the one that loads the address of our Hello World phrase into the X register. Notice in its mnemonic form it's missing something. Since we're placing the phrase data after our program, and we haven't yet finished assembling the program, we don't really know the final address of the data. We just know that it goes down here at the end of the program. So for now, the address the LDX command needs is blank. We'll come back and fill it in later. I've added a comment that what we're loading here is the address of our phrase. So the first thing we need to do is find the operation code or opcode for the LDX instruction. To do this, we'll reference the datasheet for the 6808 microprocessor. It's a set of information provided by the chip manufacturer that details how to use the CPU. And on page 15 of my version, we'll find Table 4, Index Register and Stack Manipulation Instructions. The X in X register stands for index, so we're in the right place. In the table, we find the LDX command listed, and as we read across, we see a variety of different opcodes for it. But why? It's because we can use the LDX command to load the X register from a variety of sources. We might want to load it with the contents of a variable elsewhere in memory, or a special variable stored right at the start of memory, or indirectly by adding an offset to an index. For now, all we need to know is that we'll be using the immediate addressing mode. That means that we'll be loading the value from within our own program, the 2 bytes that immediately follow the LDX instruction. If we look back at the mnemonic version, we can see that pound symbol right after the LDX and before the $sign that indicates a hexadecimal value. The pound symbol means immediate mode addressing. It means we're loading the X register with a literal hexadecimal number that we're going to write into the blank once we determine where the phrase data ends up in memory. We're loading the X register with the numbers that immediately follow the instruction. Back on the datasheet, we can see an LDX command in the immediate addressing mode has an opcode of CE. So now we can finally write down the first byte of our program in the hex column. Since we don't know the address of our phrase yet, I'll just underline the 2 missing bytes to remind us to fill them in later. So far so good. We'll get into lots more detail about addressing modes in future videos. For now, we'll take the win and move on to the next mnemonic in our program. STX stands for Store the Index Register. It takes the phrase address we loaded into the X register and puts it into the phrase address1 variable needed by the save phrase routine. In the mnemonic column, I've written the STX command and the address 0303, and I've noted that 0303 is the location of phrase address in the comments. On the data sheet, we're once again looking at Table 4. Here's the STX command, and this time we're using the extended addressing mode. This mode lets us specify a location in memory using a full 2-byte address. Note that the STX command does not have an immediate addressing mode, so that column of the table is blank. Back in the mnemonic view, the lack of a pound symbol and the fact that the address uses 4 hexadecimal digits tells us that we're using the extended addressing mode. An STX command in the extended addressing mode has an opcode of FF, so we can fill in the next line of the hex column. We write the opcode first, and we can even add the address we're storing into by copying the 2-byte address over from the mnemonic column. Well, that was practically painless. Let's see how the next mnemonic treats us. With the phrase address location loaded into phrase address 1, it's now time to call the save phrase routine in ROM. The JSR command stands for Jump to Subroutine and transfers control temporarily from our program to the save phrase routine at location 8000. Back in the datasheet, we've now moved to Table 5, the jump and branch instructions. Here is JSR, and we'll again be using the extended addressing mode to jump to any 4-digit hexadecimal address. The opcode is BD. At this point, filling in the hex column is almost automatic. The JSR command will transfer control to the save phrase routine in ROM, and Hero Jr. will speak our Hello World phrase. When the routine is done, the robot will automatically return to our program and execute the next command. RTS stands for Return from Subroutine. It transfers control back to whatever program called a subroutine in the first place. But don't be confused. This RTS is not how the save phrase routine returned control to our Hello World program. That happens somewhere else in memory, up around 8000. This RTS is the one that will return from our program back to the Hero's main menu. When we use Robot Wizard to execute a program, we're actually running it as a subroutine. So this last RTS in Hello World sends us back to the Hero's operating system. Once more on Table 5 of the datasheet, we see that RTS has only a single available addressing mode. The implied addressing mode means the command itself implies how it functions, and we don't need to provide any additional information. RTS always has an opcode of 39. And there we have it, a program to say Hello World written in machine language. We're only missing one little thing, the actual phrase information to produce the correct sounds. We'll see how to create that next, but first let's fill in the missing information we skipped over before. Now that we've assembled the program, we can figure out where in memory the phrase info will be stored. Going back to the first byte in the hex column, we just count each byte, starting with address 05D6. So if CE is D6, the next missing byte is D7, and then D8, D9, DA, DB, DC, DD, DE, and DF. Thus, the next available address right after our program is 05E0. So that's the address where we will store our phrase. The voice of the Hero Jr. robot is provided by the remarkable Votrax SC-01-A voice synthesis IC. It takes a stream of hexadecimal numbers and turns them into the sounds of human-like speech. The datasheet provides a list of individual speech sounds called phonemes, along with their matching hexadecimal values. To encode a phrase like Hello World, we start by writing down the words themselves. Here I've left some strategically placed spaces, which will make sense as we go along. The next step is to consult the datasheet's phoneme chart and begin filling in sounds that match the words. I've found it best to start with the consonant sounds, because they have the least variability. An H is always an H, and is represented by a single phoneme on the chart. So we can fill in H, L, W, R, L, and D, And by consulting the chart, we can add in the hexadecimal numbers under each one. 1B, 1/8, 2D, 2B, 1/8, and 1E. Which brings us to the vowel sounds. The Votrax chip provides a wide variety of vowel sounds in different lengths to accommodate all the different sounds an A, E, I, O, U, and sometimes Y can make in human language. Take that E in hello, for instance. Is it really just an E, a single vowel sound? Say the word slowly a few times. Hello. 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 You'll find that an E in hello is actually made of two different vowel sounds, an and an Hello. So we add in those two sounds in the spaces where the E in hello existed before. Looking at the phoneme chart, we find that there are actually multiple and sounds available in different durations, shown here in milliseconds. For hello, the best choices seem to be EH1 and UH3. Their hex numbers are 02 and 23. Likewise, the O in hello is more of a whoa sound. Hello. Let's go with UH3, O1, and U1, 23, 35, and 37, respectively. We can add a pause here at the end of hello with the PA0 phoneme. It takes up time, but it makes no sound, and it's actually required for fricative sounds like T and K and P to sound correct at the ends of words. Its code is 03. And the O in world? It's not an O at all. World. It's actually an sound. Hex code 3A. We can put a longer pause at the end of world with PA1, code 3E. And finally, at the end of any phoneme sequence, we need to include a special terminating code to let the Votrax chip know it's done its job. So we add an FF as the last hexadecimal number in the sequence. There we have it, our encoded phrase information ready to add to the end of our program. Don't let the fact that these are hex numbers confuse you. To the Votrax chip, they represent sounds, just like the hex numbers in the program itself represent commands and addresses and numeric values. The 6808 only understands one thing, numbers. Their meanings change depending on where they appear in a program, so it's up to us to keep track of which is which. The comments column is our friend. Back to our programming sheet, we can add the phrase data at address 05E0 and throw in a comment to remind us what those numbers mean. And we can backtrack and add the phrase address into the mnemonic column for the LDX command and into the hex column as well. And with that, we have a complete program ready to enter into the Hero Junior's memory. With paper in hand, we run the bootloader program at F5C4 and enter all 25 bytes of Hello World.
C, B, next, 0, 5, next, B, 0, F, 0, 3, 0, 3, B, A, 0, 0, 0, 3, 9, 1, B, 0, 2, 2, 3, 1, A, 2, 3, 3, 5, 3, 7, 0, 3, 2, B, 3, 8, 2, B, 1, A, 1, B, 3, B, F, ready.
And now for the moment of truth. We run the program at address 05D6 and...
Hello World, ready.
Well, that wasn't too shabby. And because of the way we structured the program, with the phrase data starting at a fixed location after the code, we can change the phrase to something new by just running the F5C4 bootloader at the 05E0 address instead of at 05D6. I wonder what these numbers say. So there you have it, a Hello World program running in native machine language on an unexpanded Heathkit Hero Junior robot from 1985. We'll do a lot more programming in future videos, but first we'll need to repair and upgrade the robot's single-board computer. Tune in next time for voltage pumps, memory jumpers, and a much-needed ROM upgrade. Until then,
Stay cool.
Join us next time as we continue our restoration of everyone's favorite 80s robot. And if you like this video, don't forget to
Like, subscribe, and ring the bell.